Welcome to this deep dive into a foundational challenge that, well, many of you in machine learning, data science, and technology probably face quite often.
Hmm?
How do we classify a new piece of data when all we really have are examples of data we've already classified?
Right.
It sounds simple maybe, but it underpins so many applications you might be working with.
Absolutely. I
Yeah.
mean, think about spam filters or diagnostic tools in medical imaging, even recommendation systems.
Yeah.
At their core, they often start with labeled data and need a way to assign labels to new unseen stuff.
And today we're zeroing in on a really foundational concept here. The nearest neighbor rule. It was introduced way back in 1967 in a paper by Cover and Hart.
That's the one, a truly seminal paper in the field.
And what's quite remarkable, especially for practitioners, is that this rule, while it's conceptually very simple,
Deceptively simple, perhaps.
right, but it's surprisingly effective. And it gives us a really crucial baseline for, understanding maybe more complex methods you might be using.
It really does.
Yeah.
And for those dealing with messy real-world data, the elegance of the nearest neighbor rule is its directness. It's non-parametric,
Meaning?
meaning it doesn't force you to make assumptions about how your data is distributed statistically, which, let's face it, is a huge plus when you don't know the true underlying process or it's just incredibly complex.
Okay, so let's get into the nuts and bolts then.
Yeah.
For someone maybe less familiar with the absolute basics, what is the nearest neighbor decision rule? How does it actually work?
Well, at its heart, the nearest neighbor, or NN rule, is pretty intuitive. You get a new unclassified data point.
Okay.
You look at your existing set of already labeled data points.
Your training set, basically.
Exactly. And you find the one labeled point that's closest to your new point.
Closest based on some definition.
Based on a defined way of measuring distance, yes.
Yes.
The NN rule then just says, assign the new point, the same category, the same label, as that single nearest neighbor.
That almost sounds too simple. How do you, if you're implementing this, define closest? That seems like it could be, well, critical.
Oh, it absolutely is. You've hit on a key point. The concept hinges on having what's called a metric space and choosing a distance metric.
A metric space.
It's just a set where you can reliably measure the distance between any two
Yeah.
points. And the distance metric is the specific formula you use to do that measuring.
Like the straight line distance on a graph.
That's a common one, yeah. Euclidean distance. If your data points are like coordinates on a plane, that works.
Okay.
But as the paper mentions, I think in section 2, the data points live in this metric space X with a metric D. For more complex data, maybe text data or sensor readings with tons of variables, you'd need a different metric.
Right, because a straight line doesn't make sense if you're comparing, say, documents or user profiles. You need something more abstract to capture similarity or dissimilarity.
Precisely. And choosing that right metric, that's a critical step for anyone applying this in the real world. It can make or break your results.
Got it. So find the nearest example using some appropriate distance measure and just copy its label. Simple concept. Now, the outline mentions admissibility. Why is that important for practitioners?
Okay, admissibility. This comes up when we talk about K nearest neighbors, or KNN.
Which is slightly different.
Right, it's a generalization. Instead of just the one nearest neighbor, KNN looks at the K closest neighbors. So maybe the 3 closest or 5 closest.
And then takes a vote.
Essentially, yes. You classify the new point based on the majority class among those K neighbors. Our basic NN rule is just KNN, where K equals 1.
Okay, now my intuition, and probably for many listeners, would be that looking at more neighbors, a larger K, should make the classification more stable, less prone to noise from one weird data point.
That's a very natural thought, and often it is more robust. But, and this is covering Hart's interesting finding, the simple 1NN rule can actually be strictly better than any KNN rule with K greater than 1 for certain kinds of data.
Really? Better than looking at more neighbors?
For specific distributions, yes. That's what makes 1NN admissible within the class of KNN rules. There's no single KNN rule with K1 that's guaranteed to perform better than 1NN across all possible scenarios you might face.
Huh. That's counterintuitive. Can you maybe give a conceptual example, something that might resonate?
Sure. The paper itself gives a nice one. Imagine you have 2 categories, say A and B. Category A's points are spread out uniformly inside one circle, and Category B's points are in another circle nearby but not overlapping.
Okay, 2 distinct clusters.
Right. Now picture a new data point that truly belongs to Category A, but it happens to land very close to the edge of A's circle, and maybe quite close to B's circle too.
Right on the border zone.
Exactly. Its single nearest neighbor might correctly be another point from Category A.
Makes sense.
But if you look at, say, the 3 nearest neighbors, K3, because it's near the boundary and near the other circle, 2 of those 3 neighbors might actually be from category B.
Ah, so the majority vote would then incorrectly classify it as B.
Precisely. In that specific setup, 1NN gets it right, while 3NN gets it wrong. Their figure 1 illustrates this with those uniform densities on separate disks.
Okay, that makes it much clearer. Simplicity wins in that specific case. So 1NN isn't always worse. It holds its own. Now, the next big thing is comparing NN to the optimal Bayes classifier. This sounds important for understanding performance limits.
It is, absolutely. The Bayes decision rule is like the theoretical peak of classification performance.
The gold standard.
Yes, but with a catch. It assumes you have perfect knowledge of the underlying probability distributions for every category in your data. If you have that, the Bayes rule minimizes the probability of making an error, which we call the Bayes error rate, R.
But as you said, NN is non-parametric. It doesn't assume we know those distributions.
Exactly. It works directly from the labeled examples. So the big question Cover and Hart tackled was, how well does this simple data-driven NN rule perform compared to the theoretical best, R?
And what did they find?
This is really the headline result of the paper. They derived mathematical bounds on the error rate of the nearest neighbor rule, let's call it R, in relation to R.
Okay.
For the case where you have a large number of training samples, in let's say M categories, they proved that R is always less than or equal to R.
Naturally, NN can't be better than optimal.
Right, and R is less than or equal to R times 2 minus M times R divided by M minus 1. So
Yeah.
RA, R2, MRM1.
Okay, that formula might be a bit dense for just listening. Let's unpack the M2 case, binary classification, which is super common.
Good idea. For M2, 2 categories. That upper bound simplifies beautifully. It becomes RAR, A2R, 1R.
So R less than or equal to R less than or equal to 2 times R times 1 minus R.
Exactly. Now think about what 1R means. Since R is a probability of error, it's between 0 and 1. So 1R is also between 0 and 1.
Right, which means 2R, 1R is always less than 2R.
Precisely. The error rate of the simple nearest neighbor rule, R, is at most twice the error rate of the absolute best possible classifier, R, even though NN knows nothing about the underlying probabilities.
Wow. Okay, that is significant. So this very simple method guarantees performance that's, in the same ballpark as the theoretical limit. At worst, double the error.
That's the takeaway. It tells you that a huge amount of the classification information is actually contained just in the identity of the nearest neighbor.
Yeah.
Proximity carries a lot of weight.
That really underscores the power of using distance or similarity effectively.
It absolutely does.
Okay, the outline also mentions the convergence of nearest neighbors. What's this about? How does it relate to getting more data?
This addresses what happens as your training data set gets larger and larger. Does the rule become more reliable?
You'd hope so.
And it does. Cover and Hart proved a lemma, basically a supporting theorem, which states that as the number of labeled samples goes to infinity.
Which we can approximate with very large data sets.
Right. As that happens, the nearest neighbor to any specific point X will actually converge to X itself with probability 1.
So if you have enough data points scattered around, the closest labeled one to your new point X will eventually be extremely close to X.
Essentially, yes. It becomes arbitrarily close. And importantly, this convergence happens regardless of the particular metric you're using, as long as it's a valid metric.
That makes sense. More data fills the space so your nearest neighbor gets truly near. It reinforces the idea that the local neighborhood tells you what you need to know.
Exactly. With enough data, the local evidence becomes very strong.
Now, we talked about KNN earlier, looking at K-neighbors. The paper revisits this relationship too.
Yes, it does. As we said, KNN looks at the K nearest neighbors and uses a majority vote. The intuition, again, is that using a larger K might smooth out noise and improve robustness.
Right. Less sensitive to a single outlier.
And their analysis provides some support for this intuition. They showed, for the 2-category case, in using an odd number for K to avoid ties.
Makes sense.
That the conditional risk, basically, the probability of misclassifying a point given its location, generally decreases as you increase K.
So using more neighbors tends to push the error rate down?
It tends to push it towards the optimal Bayes risk, R.
Yeah.
So in that sense, increasing K generally moves you closer to the theoretical best performance.
But wait, we also said 1NN is admissible and can sometimes be better than any KNN, so there's a tension here.
Exactly. It's a trade-off. While larger K often improves average performance and gets you closer to R, the simple 1NN rule has that unique property of sometimes being unbeatable by other KNN rules in specific scenarios.
So it's not as simple as bigger K is always better.
Definitely not.
Yeah.
The paper also derives bounds for the error rate of KNN, let's call it RK. They show RKAHAR, where JK is some function related to K. They point out that the upper bound is widest for K1, the single NN rule.
Meaning 1NN has the potential for a higher error rate in the worst case compared to some larger K values.
Correct.
But it also retains that possibility of being the best performer in certain situations. It's a nuanced picture.
Very much so.
Yeah.
It highlights that there isn't one single best value of K that works universally.
Okay, let's pull this together then. Thinking about the practical implications for ML, data science, tech professionals today, we have deep learning, gradient boosting, all sorts of complex models. Why is revisiting this 1967 paper on a simple rule still valuable?
Well, despite all the incredible advances, nearest neighbor remains relevant for, I think, several key reasons that directly impact day-to-day work.
Okay.
First, it's just so incredibly simple. Simple to understand, simple to implement.
Right, you could code a basic version pretty quickly.
Absolutely.
Yeah.
This makes it an invaluable tool for setting up a quick baseline. When you start a new classification project, running 1NN gives you an initial performance number to compare against.
A sanity check, almost. If your fancy model isn't beating simple NN, maybe something's wrong.
Precisely. Second, that non-parametric nature we talked about. Still a huge advantage when you know very little about your data's underlying distribution.
Which is common in the real world. Data is messy.
Exactly. You don't have to force it into a potentially incorrect statistical model. NN just works with the data you have.
And those theoretical bounds, like R being at most 2R, even though they're theoretical, do they still offer practical insight?
I think they do. They provide a fundamental grounding. They tell us something deep about the limits of classification, based purely on labeled examples and proximity.
It sets a context for what's even possible.
Right. It tells you how much information is inherently available just by looking at local neighborhoods in your feature space.
And for people building systems, understanding NN really hammers home the importance of what? Feature engineering, distance metrics?
Both, absolutely. The NN rule lives or dies by how you represent your data, the features, and how you measure distance between those representations.
If your idea of nearest doesn't actually correspond to points being in the same class?
Then NN won't work well. No matter how simple or theoretically nice it is, it starkly highlights that dependency.
So it motivates thinking hard about those upstream steps. Getting the right features, choosing, or even learning a good distance metric.
Exactly. It pushes you to think about what similarity really means for your specific problem and data.
So even in the age of deep learning, understanding this bedrock concept gives essential insights into classification itself.
Definitely. It's a reminder the foundational principles still hold immense value and provide context for everything else we build on top.
Okay, so to quickly summarize for everyone listening, we've explored the nearest neighbor rule from Cover and Hart's 1967 paper, its core idea, classify based on the single closest labeled example.
Using a chosen distance metric in some feature space. And importantly, it makes no assumptions about data distribution. It's non-parametric.
We discussed its admissibility, how 1NN can actually outperform KNN with K1 in certain cases.
And we covered the major theoretical result. Its error rate in the large sample limit is bounded at most twice the error of the optimal Bayes classifier. A remarkable guarantee for such a simple rule.
We also touched on convergence, how the nearest neighbor gets truly representative as data increases and the trade-offs when considering KNN versus 1NN.
Finally, we highlighted its ongoing practical relevance. A simple baseline, useful with unknown distributions, and a concept that forces us to think critically about features and distance metrics.
It really laid a crucial foundation for non-parametric pattern classification.
It absolutely did. Its influence is still felt widely, both in theory and in the systems people build every day.
Right. So on that note, here's maybe a final thought for you to take away and consider in your own work. How does this core idea of nearest neighbor of proximity show up elsewhere? Not just in classification.
Good question.
Think about recommendation systems. Aren't they often about finding items nearest to a user's past preferences or similar users?
Yeah, absolutely. Finding similar items or similar users often relies on some notion of distance in a feature space.
Or anomaly detection. Identifying points that are far from their neighbors that don't fit in.
That's another great example. Outliers are often defined by their distance to the rest of the data, particularly their local neighborhood.
So, reflect on how central this concept of defining and using distance or similarity is across so many different areas you might work in. It's more fundamental than just this one classification algorithm.
A very powerful and widely applicable concept indeed.
Thank you for joining us for this deep dive.